Hello, this is E637. I'm Charles Bouman, and today we're going to pick up on the material on IIR filters. I think we started speaking about that briefly last time, but we'll really get into some more of that material, and I think start moving on to a few other topics too. Yeah. Okay. So for IIR filters, we can move over to the yeah, there you go. The slide. Okay, so the general form of an IIR filter is that the output depends upon it has an FIR part where it depends on a window of points in space that can include both the past and the future. Now, okay, what do I mean by the past and the future in an image, right? Well, you can kind of mean anything you want, honestly. But some standard definitions are you can use this as the past, or this is the past, or that is the past, or you can use that as the past, or you can use this as the past, or you can use this as the past, or you can actually use this as the past, but you can't see through it if it was invisible. If it was a slide, you could see through it. So, or you could use you can take any ordering of the points in the plane and then call, so 1D ordering of the points in the plane and define a past and a future like that. So you could, for instance, use like a fractal curve or something. But these are the commonly used definitions of past. So in that context, an FIR filter then an IIR filter can use a window of points in the of input, and then it can only use previous output points to calculate the current, because otherwise they're not available yet, right? So, so the coefficients are the A's and the B's, and if you calculate the impulse response, okay, then you can write the impulse response more compactly like this. Here I'm using notation which simplifies things in 2D. So if I have R really means R1, comma R2, and S means S1, S2. So this is like a vector index. Now, one thing you'll have to get used to, I don't know if it's good or it's bad, but it's just the way it is, because it's the way I do it, okay? Some people don't like it, but I'm not going to change at this point, is that R here is a vector, okay? So, you know, I don't make it boldface or put a little arrow over it or anything. I just write R. And then my philosophy on this, the reason I do that is I figure that, well, you could have vectors, and you have matrices, and you can have matrices of matrices, and you have data structures of matrices, and data structures of vectors, you know. So, I mean, you can get, you know, you could put arrows and hats and tildes on top of everything. It just kind of gets out of control. So my feeling is that I define R to have some structure, and you just have to remember what it is. But I guess you can agree or disagree with it, but that's kind of the notation I use. So you need to keep track, and you know, but so S here is a vector. So if I take R minus S, that's equal to R1 minus S1, comma R2 minus S2, right? Like that. Okay. So now, the number of multiplies it takes for each output point is just the number of multiplies it takes to evaluate all this, which is basically, well, you have two windows that you have to use. The one window is, so I'm calculating the output point there, right? So I have to multiply by the points around it. So let's say this is, if you're using P previous points in one direction, then the width of this thing is going to be 2p plus 1 by 2p plus 1, right? So the total number of multiplies for the FIR part is going to be 2p plus 1 squared, right? And then, oh, I guess I used an n in my other notes. So okay, well. And then if you use an IIR part, well, that's the point you're computing, and let's say you have a little window like this. Okay. So this dimension here is 2p plus 1, right? This dimension here is p plus 1, right? And this dimension here is p, right? So, because you're using p points, I mean, it doesn't have to be defined this way, but it's kind of a standard definition. I mean, you can really do it any way you want, but using the notation of these sums, this is how it is. So, the number of and you have to multiply by a value at each of these points here. You have to take the y value, multiply it by weight, and add it back into the sum. So this is going to be 2p plus 1 times p plus, that distance right there is p, plus p, right? This is going to be 2 p squared plus p plus p. So that's equal to 2 times p squared plus p. So that's equal to 2p times p plus 1. And that's where this number is. So that's the number of multiplies you need per output point. And then if you additionally want a scale factor, I think you have to add one more. Yeah?
I don't understand why the second one, it is p, which is not 2p.
Okay, this mean there?
Yeah, the diagram or the picture that you draw.
Okay, so this first term here, 2p plus 1 times p, that's this region here. I'll draw it in red. Okay, that part there corresponds to this term. All right? Because it's 2p plus 1 wide.
The question is why vertically it is not 2p? What are you defining?
Why is this p instead of 2p? Oh, because let me see. Well, part of the answer is just the definition, right? Okay, but the other part, the reason that they picked that definition, or not definition, well, convention is probably a better word than definition. Okay, that if you pick the window, okay, you understand that if the window is a symmetric window, then this would be 2p plus 1 by 2p plus 1. You understand that, right? Okay. Then if you take that symmetric window and you take the non-symmetric half plane associated with a shape like that, okay? So now this is only p, okay? All right, so, and then this little piece that's left over here that I'll make blue, that corresponds to this, right? Okay. It's important to have an idea of how much computation these things take. So now, the computation for a fixed window size for this IIR filter isn't lower, it's higher than FIR. But with a single FIR filter, you can get a much larger impulse response, which means that you can control the frequency response in ways that couldn't otherwise be controlled. So let me just give a quick example of that. I mean, you saw that in the lab, that let's say you have a system like this in 1D. You have x of n is like this. This is z to minus 1. And this is a, right? So here you have that y of n equals a times y of n minus 1 plus x of n, okay? That's the flow diagram. This is the flow diagram corresponding to that difference equation, okay? So this is flow diagram. This is difference equation, okay? And now I can take the Z-transform of this, and I get that, well, I could either take the Z-transform or I could take the discrete time Fourier transform. But the overwhelming advantage of the Z-transform in this case is that it's a lot easier to write z than it is to write e to the j omega, okay? Because when you write e to j omega, well, first of all, this kind of symbol here is kind of squiggly, so your hand has to accelerate as it's moving around there, okay? And then there's 1, 2, 3 different symbols in that, whereas here you only have one, and that goes really fast, zip, like that, okay? Okay, so now, because remember that pretty much, okay, and hopefully there's no control theorists in the room, nor will any control theorist watch this video, okay? But because I'd get into deep trouble, they'd take me to the control theory tribunal. But basically, these are, you just take the z and you put e to the j omega. When you have the e to the j omega, you have the discrete time Fourier transform. And when you have z, you have the z transform. It's pretty much the same thing, okay? Now, the control theorists would hemorrhage if they heard me saying this, okay? Because they'd say, oh, they're totally different, okay? You know, if the thing's stable and it's causal, okay, then if you evaluate the z transform on the unit circle, you get the same answer, okay? So there's two ways. And if it's not stable, then it won't necessarily have a DTFT. Okay, so the Z transform in that sense is more general. But the other way of thinking about it is that it's like shorthand notation for the Z. Okay, but basically you just have to make sure that when you're doing things with the DTFT, that the expression you're writing are, you can get yourself into trouble if you completely ignore the theory because, like for instance, if this is the unit circle, right, that two different impulse responses can have two different signals. You can have x of n and say y of n, and x of n and y of n can have the same z transform. Okay, so they could both have the z transform, say 1 over 1 minus a z inverse. 1 minus a z inverse, and this one would be equal to x of n would say u of n times a to the n, and this will be something else, and I'm afraid to write it down because I'd have to write it down out of memory and I'll end up getting it wrong. But it's something like, well, I'm afraid to write it down. Oh, it's something like a to the n times u of minus n minus 1, and then is there a minus sign out in the front? It's u of minus n minus 1. Is that correct? No, I think this is wrong. Okay, this is wrong, but it's very close, okay? It's something like that, and I don't have time to do it. But my point is that two different signals that are different, okay? I actually think it might be this, okay? But two different signals can have the same Z transform, but the difference is the region of convergence. One case, the region of convergence is out here. In one case, the region of convergence is in here, okay? But as long as you've sat down and understood all this, okay, in the end, really, you're just replacing the Z with e to the j omega. The e to the j omega corresponds to whatever version is stable on the unit circle. So if you're analyzing the stability of systems, then using Z and Laplace transforms is very important. But if you're just trying to analyze the transfer function for a stable system, then you could really use either. Okay? So if you take the Z transform of this is going to be y of z is equal to a times z to the minus 1 y of z plus x of z. So this whole thing becomes y of z over x of z is equal to 1 over 1 minus a z inverse. And the impulse response of this thing, h of n, so this is the impulse response. H of n here is going to be just a to the n times u of n. So that's the stable that's actually, when you draw this, people always assume that you want to get the stable, you want to get the causal response of this. Okay, so if A is greater than, has a magnitude greater than 1, then this system will be unstable, because they always assume you want the causal response. But because the assumption is you're usually going to implement this in some DSP system, so you'd want the causal response, okay? But you could take the non-causal response, too. It's equally valid. Yeah, there was a point to all this. Okay, right. So this is the Ztransform, and hold on, there was some. Sorry, we got sidetracked here. Okay, so right now, hold on. Right. Okay. So we can take now. Oh, I know what I wanted to point out. Sorry, there was a point I was going to make here, and I just remembered what it was. My point is this. If you get h of n is equal to a to the n times u of n, and then y of e to the j omega, so we want to evaluate the Z-transform in the unit circle so we can actually look at what its frequency response is going to be equal to 1 over 1 minus a times z inverse, a times e to the j minus j omega, right? So I evaluated this Z-transform at z equals j omega, so z equals e to the j omega, right? Now if I take the magnitude of y of e to the j omega, that's equal to 1 over the magnitude of 1 minus a times e to the j omega, right? So, excuse me? It doesn't matter, actually, complex conjugate. Yeah, but you're correct. So this becomes 1 over, let's do it like this. We'll take it to be 1 minus a times e to the minus j omega times 1 minus a times e to the j omega, and take the square root. So that's equal to 1 over 1 plus a squared right, plus 2 times a, and then we have e to the j omega plus e to the minus j omega over 2. And you take a square root. So that's equal to 1 over 1 plus a squared times 2 cosine of 2. Oh, I kind of messed that up. It's 1 plus a squared plus 2a, and then this is cosine, minus, yeah, lost the minus sign, times cosine omega. All right? Now, when omega is 0, let's see, when omega is 0, cosine is 1. So this becomes 1 minus, this becomes 1 minus a squared minus 2a. So if a is 1, this becomes 1 plus 1 minus 2. That's 0. So this basically has a peak at 0 frequency, right? So if you look at the impulse response of this thing, the impulse response of this thing looks like this. This is h of n. So for a approximately equal to 1, of course, a has to be less than 1 and greater than 0, say, for simplicity. But let's say it's close to 1. then the impulse response looks like this. It decays very slowly. Like that, right? So if that decays very slowly, what do you know about h of e to the j omega? Well, first of all, at 0, h of e to the j 0, that's going to be equal to, we calculated, 1 over 1 plus a squared minus 2a. So that's going to be large. So that's large because this sum is large, right? Remember, the amplitude at 0 is what? It's the sum of the impulse response. So remember, that's the recurring theme. So it's going to be like this. I mean, I'm just drawing it. And over here is going to be, say, pi minus pi. So if you were going to implement this as an FIR filter, getting very sharp, you see, in the frequency domain, this has a very sharp structure to it, right? Anything that's small in frequency is large in time. Anything that's large in time has small in frequency. Yeah, that's basically true. So this is small in this dimension, so it's got a very long impulse response. If I wanted to implement this as an FIR filter, I'd have to take a very large window to get a good approximation. But I'd need a very large window in time because the structure and frequency is very fine. So a larger window in time gives me more fine sampling in frequency, is one way of thinking about it. So right now, I can implement this filter with I can implement this filter with 1 multiply per pixel, or 1 multiply per time point. But if I implemented this as an FIR filter, it could be 1,000 multiplies per pixel. So this is something very fundamental. One thing it teaches you is that in signal processing, sometimes there's 2 methods that are equivalent, but one can be implemented with very low complexity, and the other one can be implemented in very high complexity, okay? Often it's the case that the obvious thing has high complexity, and the unobvious thing has low complexity, okay? It could work the other way around, but what happens is if the obvious thing has high complexity and the unobvious thing has low complexity, if the obvious thing has low complexity and the unobvious thing has high complexity, then you just wouldn't even bother having the discussion. It'd be like, well, if you didn't do that, you'd be kind of like silly, right? So here, but often by having sort of an insight into the problem, you could do better. And this is an example. So IIR filters, the reason people like them is because they can reduce computation to achieve the same frequency response. But the price you pay for that is the design of the filter tends to be a lot more complicated because you have sort of your control of the filter response is indirect. You're sort of it's a nonlinear relationship between A and the impulse response. The impulse response shows up. A shows up as a parameter in the impulse response in this form, and that's not a linear form. So optimizing the impulse response through the choice of this parameter becomes a more complicated problem. But one that may be valuable to do, it may be worth it to you in an application because you can save a lot of computation. Often you have this trade-off between computation you do up front and computation that you have to use online. So if you can do a lot of computation up front so that you can design something that's very low computation when it's actually used, that's often a good trade-off. It depends how often you're going to use something. If you're only going to do it once, then it's not worth it. But if you're going to do it millions of times, then it may be a very favorable trade-off. Okay, so the rest of this I think is pretty straightforward. I mean, I think, and especially since you did the filtering lab, I think that you should sort of be able to go through it. This is an example. I just worked an example. So this is the same kind of example, only we have Z1 and Z2 for taking the Ztransform. in 2D, okay? Here's a sort of a particular example, and you can see the impulse response kind of is long. And now the impulse response in 2D is, now this is an important point, that the impulse response parameterized by this filter. Okay, so this is a single filter for a particular choice of A, right? Or we could have actually had two coefficients. We could have had a coefficient for A1, and this could have been A2, all right? Now, but if you look at the family of filters that are parameterized by these coefficients, right, that family has characteristics, okay? So any individual in the family has characteristics, and the family itself has characteristics. Now, a particular filter in this family can be designed, or in maybe a slightly extended family. In fact, you had this in a lab question. You could design the filter so that it's symmetric in frequency. So this shape here is not actually symmetric, but it's not too far from symmetric. It has clearly an orientation along this direction, right? And that's because you use this ordering in raster ordering. So it inherited the orientation of its raster ordering. But you can design filters that use raster ordering that have symmetric frequency responses. It's possible to do that. They exist, and there was one actually in your lab, I think, that had that property. But the family does not have symmetric properties. That's to say that if you take one filter that has, say, a particular orientation like this in this family, and you take the filter and you rotate its frequency response by 90 degrees, that new filter will not be in the same family, or may not be in the same family. So, so this orientation of the raster ordering imposes certain anisotropic behavior to the filter. Anisotropic means that the behavior is not independent of orientation. Isotropic means if something's isotropic, if a material is isotropic, then you would say its behavior is independent of orientation, right? So, for instance, is corrugated cardboard isotropic? No, because everybody knows the corrugated cardboard has little folds in it along one direction, right? So it's easier to bend it that way than it is the other direction, right? So it's not an isotropic material. Any crystal is not an isotropic material because there are crystal grain boundaries that it will break across, right? But so this filter is not isotropic because it doesn't have the same properties in all directions, right? And actually, in a 2D discrete grid, you can never have a truly isotropic filter because the grid itself is not isotropic. If you do a rotation of the grid, it's not isotropic. But you can approximately be isotropic. But things that are not isotropic are called anisotropic. So anyway, so the take-home message is that it's sort of an engineering message, which is that, okay, for IIR filters, well, so if you have an FIR filter, you use all the pixels around the point, okay? The advantage of an FIR filter is it's isotropic and it's it's simple to implement, at least in concept, okay? So the pluses is that it's simple and direct, and designing it is straightforward. You pick the frequency response you want, you take the inverse Fourier transform to get the impulse response, and you just window it with, say, a Hamming window. But the downside of it is the computation can be massive for implementation, right? The upside of the IIR filter is that it can have much lower complexity to implement. But the downside is that it's you inherit, first of all, the design problem is more difficult because it's a nonlinear design problem. And second of all, that the response of the filter inherits the intrinsic anisotropic behavior of the raster ordering. Right? So inevitably that tends to produce problems that well, not always, but often it tends to produce problems that have to be fixed. Okay? So there's, yeah.
Is this equivalent to nonlinear phase in time domain filter?
Yes. Okay. So an FIR filter can be designed to have, well, it's not equivalent, but it's related to. An FIR filter could be designed to have linear phase. So perfect linear phase. So the simplest linear phase filter is one with 0 phase. Okay. So if this is a symmetric filter, if this is a symmetric function, so if h of mn equals minus h of minus h of minus m minus n, okay? If this is the case, then the filter's phase is 0. There's a slight caveat there, okay? Which it's 0 phase, but the real part may be negative, okay? But I'm calling that 0 phase, okay? So that's a linear phase filter, and then if you delay that by a fixed amount of time, it's linear phase. An IIR filter generally can't be designed to be perfectly linear phase because you can't get a perfect symmetry to the impulse response. You can get close to linear phase, and that becomes a numerical optimization problem. But if you need perfect linear phase filters, then you usually use FIR. Okay, now, there's one last thought I want to leave you with. I'm going to skip some of this and figure you'll go through it yourself. Okay, the one last thought I want to leave you with, just to confuse you after everything I said, was that, well, why can't you have an IIR filter that depends upon the pixels both before and after it?
You haven't done this
Yeah,
yet.
so it's clearly impossible, right?
That look says no.
Yeah. No, it's really not impossible, right? I mean, because you could do the following thing. You could say, okay, I'm going to have y of n, say, equal to, say, a times x of n minus 1 plus x of n plus 1, right? And you'd say, and then plus x of n, say, or something like that, right? So you could have this, all right?
Oh, I thought you meant you couldn't do y in the future, though. Right.
Oh, I'm sorry, y. Yeah, that's what I meant.
Oh,
I wrote the wrong thing. Yeah, I did write. Yeah, what you thought was correct.
Okay.
Okay? And you'd say, see, this is an example of where we teach you things. We subliminally, we're like some kind of mind control organization. So what we do is in engineering, we teach you things subliminally. We never say they're true, but we imply they're true. And we let you think they're true, okay? Because it serves our evil needs, okay? So the thing is that, so we've always kind of implied that this was impossible, right? Obviously, it's possible, right? It's got to be impossible. Who thinks it's possible? But you do it all the time, okay? Okay, here you go. So what you do is you just say this. Okay, so y of n, we'll set it up as a vector. So this is y of 1, and this is y of n, right? And then this is a matrix, right? And the matrix is, okay, there's 1s on the diagonal, right? And I guess here we got an A. And here we have an A. And here we have an x1, and here we have xn. Right, that's the same equation as that. Right? So I can make this A. Oh, I'm lying. I keep doing this. Okay, yeah, but it's still true. Okay, let me do that one more time. That is different. Okay, so this is y. Oh, I botched this so badly, I'm just going to have to rewrite it. Okay, y of n. Y of n minus 1 plus y. You're still hoping that it's not possible, right? You're figuring, oh yeah, he just keeps doing it wrong because it's not possible, and he's going to realize that in just a moment. Y of 1 through y of n. By the way, very soon I'm going to show you something else that's true that's not possible. Hold on. This is 0. This is A. This is y1 through yn. This is x1 through xn. so that's true, right? And then this is A, right? This is Y. This is X. And this is X. Oh, this is Y. I keep doing that. And this is X, right? So the equation here is Y equals AY plus X, right? So this is also I times Y, where this is the identity matrix, right? Mm-hmm. So this is going to be I minus A times Y is equal to X, right? So Y here just equals I minus A inverse X, right? And for some values of A, Y is an invertible. This is an invertible matrix, and for some it's not. Mm-hmm. But that's just a stability condition. Okay. So you could do that, right?
Yeah.
But so that's actually a generalization of an IIR filter to non-causal dependencies. The problem is implementing this is computationally expensive. Actually, if you recall from your linear algebra, I don't know if you know this, but linear algebra is related to what you actually do. So from your linear algebra course, you know that lower triangular matrices are easily invertible, right? Or upper triangular matrices are easily invertible. That's the same reason you can implement an IIR filter, because you can inversion of a lower triangular matrix is basically the same as implementing an IIR filter. But if it's not lower triangular, then the inversion is more complicated. And you have to use, Gauss elimination or whatever, any number of numerical techniques to do the matrix inversion. But you can, in principle, do it. And as a matter of fact, this topic actually becomes important because there are important benefits to this model. That the parameterization here is low, but it gets rid of the fact that you have a problem with anisotropy. Okay, so this could be used to make a filter which is much more isotropic. You only need 1, 2, 3, 4 parameters to implement it, so the number of parameters is small, as opposed to an FIR filter where you'd have a huge number of parameters. Now, the bad news, though, is the computation's high, because you have to invert a matrix, and a matrix inversion is order, for a general matrix, is order n cubed, I think, right, where n is the dimension of the matrix. So matrix vector multiplication is n squared. I'm sure it's at least n cubed. So for matrix inversion, so that's high. If it's a Toeplitz matrix, it's easier. I don't know, how many people took 630? No, this is 637. Yeah, hold on. 538 is it? Oh, I'm getting all mixed up. The signal processing course. It's
DSP.
DSP 538, right? Yeah. How many people took 538? So you did inversion of Toeplitz matrices in there, I bet, right? Didn't you? Don't you do the? Oh, you didn't do the fast algorithm for least squares filtering. What is it called? They don't cover that anymore. What is it called? Oh, I bet you did it and you just forgot. You didn't realize it was the Toeplitz matrix you were inverting. Okay. The excuse me? I'm sorry. Say it again. Yeah, when you did AR processes, did you do?
We actually didn't cover them.
Oh, you didn't?
No.
Oh, okay. Okay, well, actually, that's kind of good because we cover them in here, so you learn it somewhere. Okay. So that's a nice segue into the next topic, which is going to actually include AR processes. Okay, so random variables. You thought you had avoided them. Random variables are just terrific, okay? Because really, well, first of all, I'm biased, but I'm highly biased, but I think one of the things that is so powerful about electrical engineering, okay, really the most important concepts of electrical engineering, I'll include computer engineers too, electrical and computer engineering, right, is the idea of a module, okay? And you learn about, like in your introductory circuits course, you learn about Thevenin and Norton equivalents, where you have a box and you put something into the box and you measure something out of the box, right? And inside the box, you can have monstrously complicated things, okay? This could be like a human cell, okay? Okay, or it could be the United States economy, okay? Or it could be like, it could be a galaxy, okay? Of course, it's hard to put inputs into the galaxy. But it could be all kinds of things, right? And so the beauty of electrical engineering is you can take a monstrously complicated thing, okay? And you can just say, well, this is X, and that's Y, and the relationship is f of X of Y, okay? Fine. I mean, it's good. Now, so this is a very powerful concept, and it's, broadly referred to as a model. So there's a lot of very powerful concepts. If you can model things, then you can often do very valuable, you could do important information processing tasks with those models, okay, which use those models, okay? But one fundamental deficiency is that in real life, the output is not always just a deterministic function of the input. In fact, in real life, the output is almost never a deterministic function of the input. There's usually some kind of noise or uncertainty or something, right? So one of my favorite analogies is parents, okay? So if you wanted to model your parents, right, you put some sort of input in here, you're never quite sure what that output's going to be, right? Could be a wide range of things. So your text messaging could get turned off, right? Anything could happen. So you need to actually model that uncertainty in the outcome. And that's where random variables come in. That this thing here isn't just a deterministic function. It needs to be a random variable. So this is a random variable. So random variables fill a huge hole in engineering, because without them, it's very difficult to model uncertainty. There are other methodologies for modeling certainty, but I think probability and random variables have become the widely accepted sort of method of choice. Okay. Now, so it's a very, very powerful concept, and it takes a certain amount of time to get used to. You kind of have to learn it a few times. Okay, so I'm going to go through this very quickly because I'm assuming most people have taken 600. Now, what happens is that, well, first of all, random variable, well, the definition of a random variable is somewhat complex, so I'm going to sidestep it. But basically, a random variable is actually a function. It's a function from a probability space to the real line. So you have some probability space, omega, okay, and you have a function, x of omega, okay, where omega is a member of omega, okay, and that function then maps to the real line, I guess. Maybe I shouldn't have drawn it this way, because usually the real line is horizontal, but this would be the real line, okay? And that's a random variable. And then if you want to ask yourself, well, what's the probability that x is a member of some set, I don't know, set A, okay, where A is a subset of the real line, then what you really do is you ask yourself, well, okay, what's the probability, right, of the set of omega, a member of omega, such that x of omega is a member of A. So this thing, so you take some set here, okay? Let's say it's a closed interval on the real line. We'll call it A. And you look at all the values in omega that map to that A. So this is sometimes denoted as x inverse of A, because it's the set of all omegas which map to it. That set there can be formally denoted as the set of omega, a member of omega, of x of omega, a member of A. All right? And then the probability measure is really it's a measure on this space here, not on R. So you write, okay, P of X inverse of A. So if you didn't already understand this before I started talking about it, it's kind of unlikely you would have picked it up just at this moment. Okay, so if this feels a little difficult to understand, well, I would encourage you to go back and try to understand it at this basic level, or to review your 600 notes. Okay, but I at least feel an obligation to just touch on it. Okay, so the idea is the probability is a measure on this underlying space, and now it obeys certain rules. Okay, and there's certain places you can get yourself into trouble here, and a lot of probability from a theoretical perspective is dedicated to eliminating all the really bad things that can happen. Okay, so one of the really bad things that can happen is if you take the union of an uncountably large number of elements in a set, then you can make all kinds of really bad things happen. So here's an example. Okay, so we'll take a thing called, let's define our probability measure, okay, to be length on, say, and our set, our subset, it'll be length on the unit interval 0 to 1, okay? All right? So the probability of the set, say, I don't know, 0 to 1/2, that's 1/2, okay? And the probability of the set 1/4 to 1/2, say, that's 1/4, okay? Because it's just the length of the set, okay? Now, what's the probability of the set 1/4, 1/4? 0, right? Does anybody disagree? No, okay? It's because, right, it's obvious, right? Now, if I take the union of all A in the interval 0 to 1 of the set, of the set 1/4, or closed interval, I'll make it 1/4. Oh gosh, I'm really messing this up. Hold on, let me just redo this. I'll keep this and I'll just do it on another piece of paper. If I take the union of the set A, a member of 0, 1, of the interval A, comma A, and I define that as, okay, well, first of all, what's that?
Should be the whole set.
That's just the interval 0 to 1, right? Because if I take the union of all points on the interval 0 to 1, I get certainly the interval 0 to 1, right? Okay, so if I take the probability of the interval 0 to 1, what's that equal to?
1.
1, okay. Now, if I take the probability of the union of a member of the interval 0, 1, what's that equal to?
0.
It has to also equal 1 because this equals that, right?
Well, it's supposed to.
Well, no. I mean, this is irrefutable because that set. See, these two sets, that is equal to this, right?
Yes.
So the probability of this has to be equal to the probability of that.
But each of the individual probabilities of the A to A is 0.
That's correct.
Right.
Okay, but this has to equal that, right?
Yes, by definition, yes.
By definition, right? But but you would like to say that the union over A what's that equal to?
It's not equal to the, yeah.
That's equal, I'm sorry, this is a sum. you would hope that this would be a sum.
Right.
Okay, I'm running out. That this is equal to the sum of 0 equals 0. So we proved 0 equals 1. So the problem is this. This is not equal to that. So you want to avoid uncountable sums of sets when you're doing probabilities. So we'll pick up on the probability next time with some more details, but I'm just sort of doing the basics very quickly. Thanks a lot. See you on Wednesday.